talking about finding derivatives using all these shortcut rules. Now remember, a derivative is a rate of change, an instantaneous rate of change. It's also the slope of a function at a point. And if you remember, the long way to find the derivative of a function is to find the slope between 2 points and then find the limit as those 2 points get infinitely close to each other. We call that the limit definition of the derivative. But that's pretty onerous when you're taking derivatives of complicated functions. So we have discovered all of these different shortcut rules in class. The power rule, the trig rules, exponential rule, product rule, quotient rule, and then the coefficient rule. So I'm just going to do a quick example of some of these, and then we'll do some problems. So an example of the power rule, I think most people are comfortable with this. If I have x to the 7th, right, then my derivative is just 7x to the 6th. The thing that's tricky with the power rule is sometimes if I have a tricky thing, like let's do another example. Let's say I have y equals 1 over the cubed root of x. Well, before I can use the power rule, I have to rewrite this so it's in the form a times x to the b. The power rule only works when a term is in the form a times x to the b, where a is a coefficient, x to some constant. So what I would do in this instance is I would first rewrite this as x to the negative 1/3, right? This is the same as 1 over x to the 1/3. Then I'm bringing x to the 1/3 up into the numerator so the sign changes. And now I'm ready to take the derivative using the power rule. So that would be negative 1/3 times x to the negative 1/3 minus 1. So negative 1/3 minus 3/3, which would be negative 4/3. That's our power rule. There are other videos on that. The trig rules are pretty straightforward. The derivative of sine is cosine. Derivative of sine is cosine. Cosine, cosine. Derivative of cosine is negative sine. And tan is secant squared. Hey, that's pretty straightforward. Exponentials are a little weird because of that natural log. I'm just going to erase this example so I have room. You guys can rewind if you need to see that again. So for example, if I had y equals 2 to the x, that's an exponential term, right? The derivative of that would be the natural log of 2 times 2 to the x. All right, pretty straightforward. Now the thing that's cool is if I had another example with y equals e to the x, I can follow that rule. The derivative would then be the natural log of the base times e to the x. Oh my gosh, the natural log of e is 1. Natural log of e is 1 because e to the 1 equals e. So the derivative of e to the x we discovered is e to the x, which is this mind-blowing, beautiful thing about e. The rate at which e is changing, e to the x is changing. The slope of the function is equal to the y value at that point. That's mind-blowing. Okay, the product rule is just that. When I have a function of something times something, it's the derivative of the first times the second as it is, plus the first as it is times the derivative of the second. And sometimes we have to do some simplifying, but sometimes we don't. Let's just say I have x to the 3rd times sine of x. Okay, I have two different functions. I can't simplify those in any way. So I'm going to take the derivative with respect to x. So it's the derivative of the first times sine of x as it is, plus, boom, a, x to the 3rd as it is, times the derivative of my second piece. The derivative of sine is cosine. And when I look back at that, there's really not much simplifying I could do. So I just took the derivative of that and I'm good to go. All right? So too with the quotient rule. Let's do an example. I might run out of room here. If I have y, so I'll just do a short one. If I had y equals, x squared over the cosine of x, my derivative is going to be the derivative of the numerator. So the derivative of x squared is 2x times the denominator as it is minus the numerator as it is times the derivative of the denominator. Ooh, this is a little tricky. The derivative of cosine is negative sine. So this is going to be x squared times negative sine. A negative times a negative is a positive, so that's going to become a plus. This is a little sneaky, over the bottom squared. Okie doke. The coefficient rule is just a handy thing. When you have a coefficient hanging in front of any function, the derivative is just the coefficient times the derivative of that function. So an example, if I had y equals 4 times 2 to the x, right? That 4 is the coefficient. So when I take the derivative, that 4 is just going to hang out 4 times the derivative of 2 to the x. Well, the derivative of 2 to the x is the natural log of 2 times 2 to the x. So it's going to be 4 times the natural log of 2 times 2 to the x. So here are kind of our basic rules. We haven't learned about the chain rule yet. That's the next big rule we're going to be talking about. But here are some basic shortcut rules to find the derivative.
A man walks down
All
the
right.
street, he says, why am I
There are
so...
a couple things I could do. I could distribute that 3 to the x, but since this is an exponential term and that's a polynomial term, that's not going to make things much simpler for me. I think I'm just going to do the product rule. I'm going to consider this A, I'm going to consider this B, and I'm going to find the derivative of that product. So if we remember, the derivative of a product is the derivative of the first times the second as it is, plus the first as it is, times the derivative of the second. So here I go. The derivative, hey, I'm in a Leibniz mood. This is Leibniz's notation for the derivative. I could have used y prime. They're interchangeable. Okay, so the derivative of A, that's an exponential term. So I think of my exponential rule. So it's the natural log of the base times the exponential term as it is. So that's the derivative of A times B as it is. I need parentheses here because B is a 2 terms. Plus A as it is, easy enough, times the derivative of B. Okay, so the derivative of B, I'm going to take the derivative of each term. So that's going to be derivative of x squared, which is 2x, plus 5. All right? And I'm just going to leave it like that. What do you think? Let's just leave it like that. All right, let's look at some other examples. Let's take the derivative of another couple of examples. So here's a kooky function made up of 3 separate terms. So when you take the derivative of a function, you can take the derivative of each term. So when you face each term, you just ask yourself, what kind of function is that? If I were looking at that one term as a little function, what type of function is it? How am I going to take the derivative? What rule am I going to use? All right, so I'm going to take this derivative with respect to x. I'm using my Leibniz notation. Again, I could just have said y prime. The derivative of 4 times 2 to the x, that is an exponential term. So I need to use my exponential derivative shortcut. That 4 is a coefficient. So the derivative of a coefficient times a function is just that coefficient times the derivative of your thing. So derivative of 2 to the x is natural log of 2 times 2 to the x. There we go. All right? Now, lots of times people say, well, can I simplify this? And the answer is no. The natural log of 2 is that's an irrational number. If we were scientists and needed a decimal equivalent, then you could do 4 times the natural log of 2 in your calculator and get a decimal approximation. But 4 times the natural log of 2 is the exact way of writing that expression. So that's now my coefficient of 2 to the x. All right, let's continue. Minus the derivative of cosine x is negative sine. So that's minus negative sine of x. Hey, minus a negative gives me my positive, so that's going to be plus sine of x, plus, here I have a coefficient of 6, that's just going to hang out, times the derivative of tan. The derivative of tan, as we know, is secant squared x. So there we have it. I just took the derivative of each term. All right? Let's try a quotient rule and then call it a day. So let's say that I have a function, I'll call it f of x, and it is, I don't know, let's say e to the x minus x squared is my numerator, and my denominator is going to be 3x minus 1. A kooky looking function, I'm sure, if we graphed this. I want to take the derivative. There's clearly nothing I can do to simplify this. I'm going to use the quotient rule. And if you recall the quotient rule, if I'm taking the derivative of something with a numerator and a denominator, that derivative is the derivative of the numerator times the denominator as it is minus the numerator as it is times the derivative of the denominator over the denominator squared. So here I go. The derivative of the numerator. Well, the derivative of e to the x is e to the x. I love that. Minus the derivative of x squared is 2x. All right, I did a prime times b as it is. These parentheses, of course, are essential here. Minus a as it is. So I'm going to run out of room here. A as it is my numerator as is times the derivative of the bottom. Derivative of 3x minus 1 is just 3 all over the denominator squared. Okay? Now, if these were all nice polynomials, I might distribute and combine like terms, but I've got e to the x there. It's kind of kooky. I'm just going to leave this as is for now. My denominator, I'm certainly not ever going to want to expand that out. But that's my quotient rule in action. All right, I hope this was helpful.
Why am I soft in the middle? The rest of my life is so hard. I need a photo opportunity. I want a shot of redemption.